So we're going to start with what is acceleration. What is acceleration? Ready, go. Speeding up. Anybody else? Okay, so every class of students I have ever asked in the history of me teaching physics, physical science, or anything else, when I ask that question, every single time that is what every single student has said, speeding up. Okay? Which is correct. However, the sciencey definition of acceleration is a little bit more expanded than just speeding up. Right? And I think you just said it. What else is acceleration? Changing speed. So what other kinds of changing speed can we have other than speeding up? Slowing down. And more generally, because when we're talking about acceleration, we're talking about changing not just speed, but we're going to use the word velocity. Right? And velocity is a scalar quantity. That means it has not just magnitude, like 20 miles an hour or 10 meters a second or whatever, but velocity also includes direction. So here's where acceleration just gets a little weird, right? So if I walk at a steady pace of 1 meter per second, right, and I turn and I'm still walking the same speed, I am still going 1 meter per second, but as soon as I do this and turn, has my velocity changed? What do you mean? E? So has my speed changed in the last minute? No, I've been going 1 meter per second in the last minute, but what has changed? My direction. So if my direction changed, what changed? Not acceleration. Well, technically true, but velocity. Right? Since velocity includes direction, so acceleration can be speeding up, speed down, and change direction. Speed up, speed down, change direction. All of those are acceleration.
Do we have to put speed down?
Speed up, speed down, change direction. You can write it however you want. And in truth, you probably should not use the word speed. You should use the word velocity, but speed is the more common term. Velocity up, velocity down, and also change direction. So, because this is physics, guys, all right, so because physics, there's going to be an equation, because of course there is. So the equation for acceleration is going to be a change in velocity over a change in time. Now, how are we going to write this, though, in a physics class? Are we going to say change in? What are we going to say? Delta V over delta T. When have we seen an equation that looks very similar? For what? What did the velocity equation look like? Delta D over delta T, yes. So that's where we're going next. So make sure you get this in your notebook. I think everybody's got this in their notebook. So let's go back in time and let's talk about graphs. How would you describe the motion pictured in this graph?
Linear.
Okay, linear graph, sure. What do you mean? Constant what? Constant velocity, constant speed. Why?
Because it's not changing direction. Because it's only one segment.
It's only D and T.
Well, it describes velocity though, does it not? Well, think of our equation. You guys just said it a minute ago, right? What's our velocity equation? Right? I guess you can add the delta in here if you'd like. But velocity relates these two things. Right? Who remembers from algebra how we define the slope of a line? Rise over run. Keep going.
X over Y.
Not just x over y. Y equals mx plus b is the formula for finding the slope of a line. But how would we actually define slope then? If we wanted to figure out the slope of this line, what would we need? 2 points? And then what would we do with those 2 points? Calculate it. The change in what?
Between the Y and X.
And then how would that equation look? Does anybody remember this?
Y2 minus Y1.
Yes. All right, so slope of a line is the change in y divided by the change in x. How is that similar to our formula right above it? Let's clean this up a little bit. How does that relate to the formula for distance over time that we just found? It's the same, right? Change in y over the change in x, change in distance over the change in time. The slope of a line on a distance time graph gives you what? Velocity. So take a second and think about this. This is the point. This is how physics and math and how we describe and relate things together, how these are all intertwined. That now the slope of a distance and time graph gives us velocity. And in this case, somebody said it earlier, this particular distance and time graph looks like some kind of constant speed going away from the motion detector in the case of our Investigate, right? So let's keep going. In your logbook, maybe draw it a little bit better than I just did. I want you to draw 2 graphs. I want you to draw your first distance and time graph like I did. Guys, I'm losing my patience with this table in the back right. So you guys figure it out. So draw this distance time graph on the left. And I want you to draw in your notes, next to it or below it or whatever, a velocity and time graph. And I want you to show me what you think the velocity over time graph would look like that corresponds to the motion on the left. What would the velocity over time look like if that is your distance and time graph? What would these two things, they're related. We're talking about the same motion here, right? So if your distance over time is this straight angled line, what would the velocity over time graph look like that describes the same motion? Okay? This is you? No? Think about this.
Did you do the same?
I will spoil it for you. It does not look the same.
Is it invert?
So if this is velocity over time, what are you saying with this graph? How would you read this? Like you did here. This says what? Distance moving away, right? And increasing over time? So how do you describe this?
Divided by time twice.
How would you describe this? This equals,
It's
Speed divided
speed
by
down.
t divided by t n.
is that what this says though?
Well, you put the opposite on that. Yeah.
I agree, yes. But is that what this is? Is that what's happening here? Is it?
It's steady. The motion is steady. It doesn't change.
Okay, you're drawing some fancy curved lines.
Square.
This kid here, sciences.
I want to say I want
This kid, sciences.
Do we have to focus that
Nope.
squared?
You know what that makes sense.
Nope.
I mean, never know.
Let's
It's either just like half the line.
let's think about this. Describe this motion for me again. Someone just describe it. Just like you did on the quiz the other day, right? We had those graphs, and how would you describe this motion? Away at a constant speed. How would you, what are we trying to describe in this graph? Speed over time. So what did you just say about the speed of that in that graph? Constant speed. How would we draw a graph of constant speed? Speed that is unchanging would be a graph that looks like what?
A line. Horizontal.
This is the jump in your mind of thinking about what we're talking about. Right? You said it. You guys, honestly, on the quiz, almost everybody got that section right at the top of describing the motion in those graphs. And they were harder than this. They had multiple segments. Right? So just read it aloud to yourself. Oh, yeah, moving away at a constant speed. You're right. So how would we graph constant speed on a velocity time graph? It would just be a straight line. Right? This is the jump. This is where you have to think about what we're looking at. Think about what it means. How, if you're saying constant speed, okay, I agree with you. That's right. How would we graph that if we had velocity and time? And you're absolutely right. That would be a straight line across. So let's make it weird. In your investigate, I should do this with, come on. E, get the phone. So, you know, it would be when I'm recording the video too, right? Like that's when the phone's going to ring. It's not even for me. He's redirecting the call. Was that a call from Miss Z?
No. They're trying to get some to see though.
Yeah.
Why would they call you then?
Because our phone numbers got switched because we switched rooms. So my number came with me, and it's the same. It's complicated.
This number's got changed.
All right. So here we have a graph that looks like one of the graphs from your investigate. Does it not? You guys have seen this on your investigate. How did you, or have you, how would you, how do we describe this motion?
Walks away slowly, then speeds up really quickly.
So in the quiz the other day, we had this exact kind of sort of thing, but there was a difference between the one on the board and the one that you answered on the quiz.
That one, it was like they were going and then there was a sudden change, and this one's accelerating.
Ah, acceleration. So let's see if we can see what this means. So I'm going to break this graph into segments so I can kind of define out what this looks like. And again, this is a general graph, just distance and time, and I drew a line. I didn't have data for this. I'm not plugging this in. But for the sake of this, we're going to try, and I'm real bad at this. You guys know my art skills. I'm going to try to do even segments here. So we are going to break this graph into several different segments and find the average velocity in those segments. And again, how do we find velocity? What's that formula? Okay, so I'm going to break this graph into some pieces. Those pieces are going to be 1 second apart. You may want to try and draw this in your logbook. I don't know, let's pick some distance numbers here. Let's call these meters to make it easy, and this seconds to make this easy. But all I did is just draw a shape, and then I'm just kind of putting some bogus numbers in here just so we can look at what happens on a curve like this and how we can define it out. None of this is going to be very exact or sciencey, but you guys will kind of get the point. In your logbooks, as you're doing the investigate, you're going to have a chance to do some of this that's a much more accurate picture because you have actual data tables. So here we go. In the first second, right, we're just going to call this segment 1, segment 2, segment 3, and segment 4. I don't think we'll need to get to 5. In that first segment, so from time 0 to time 1, how would we calculate our average velocity over that time? Remember our formula for velocity, right? So for V1, how do we calculate the average time in that segment? Distance over time. Good. So our time is going to be pretty easy because it's just 1 second, right? How do we find our distance for segment 1?
Draw like a line.
Ah, what do you mean by that?
Draw.
Yeah, just kind of do this, right? Again, there's no real science here. This is not very accurate or whatever. But for the sake of this, if you were doing this on a real graph, you'd have some data here. So what would our distance here be? How do we average that, do we think? What's our estimate?
3.
3 or 4?
Guys, stop. 4.
All right, it's 4. So what's our velocity in segment 1?
4 meters per second.
4 meters per second. How would I calculate my velocity for segment 2?
Draw another line.
Okay.
This R.
So segment 2 is at time 2. 8? We're agreed on 8?
I wish you were emo.
So remember, velocity is v final minus v, not v. Come on now. Distance final minus distance initial over the time, which final minus initial here is going to be 4
Minus 4.
divided by 1. So over the first 2 seconds, what has my velocity done?
Nothing.
Not much, right?
Yeah.
And does that pan out looking at the shape of the graph? Right? Look at those first 2 segments. Why do I suspect the time on those, the distance over time, is similar on those? Look at that portion of the line that we drew. Right? It's close to the same. Let's keep going. Segment 3. Velocity 3. So now what is our time is still 1. What is our distance for segment 3? 8 to 17. Can I get an 8 to 17 maybe? 18? We got an agreement on the number for segment 3?
That'd be over 30.
16, 17. I'm going to say 17. So 17, where do we start segment 3 at?
30.
No, what was this number here? 8? 17 minus 8 equals what? 9 divided by 1. What happened to our velocity? It went up. Does that pan out looking at the graph? Yeah. All right, let's try our last point here. Our last segment. All right, what do we do now? 17 to 28. 28 minus 17 over 1 equals. If we did the math, what do you think might happen in segment 5? What pattern do you see developing here? So what's happening to our velocity over time? It's increasing. Now, again, there'd be better numbers here if we had real data and a real graph and a real teacher that could draw straight lines and straight dotted lines. Unfortunately, you guys are stuck with me instead. But you can clearly see if we had to draw a velocity over time graph for our situation here. What would this graph look like? Would it be a straight line again? Why not? What was happening to our velocity over time? Again, it wouldn't be a straight line with our data because this was just a crummy drawing on a whiteboard. But it's less important for our purposes here when we're just discussing it, that the numbers are accurate. It's more important that you understand kind of the concept behind this, right? And all we started with was just a line on a graph. That's it. In this case, it was a curved line, right? In your notes, I want you to work out what this graph would look like. Given the distance and time on the left, what would this look like? And feel free to break it down into chunks or think about it like we just did the last problem. Yeah, up here. Do that on the next page. I know, it's a fresh page, E. I feel your pain here. So, like I did, break it into a couple chunks.
What is that?
Well, like we just did before, right? Where we did this. Break this graph into those little pieces and kind of do some of this, and you'll see what that graph looks like. You'll see what the velocity is doing, right? And then if you know what the velocity is doing, then you can kind of sketch how that graph would look, right? Think about what we said here, right? So move your elbow, bro. So what do we say here the velocity was doing over time?
Doesn't change.
Doesn't change. What do we say the velocity over here was doing over time? Increasing, right? Because of how that graph looked. So now break this apart. Is it staying the same? Is it increasing? Maybe it's doing decreasing, right? Like what's happening to the velocity over time on this graph? Catch that? Where you at?
I'm done. I don't know. That's not right, but I put that down.
So this and this was this.
Yeah.
So you would posit that both of these lines end up with the same thing here?
I use my better judgment and I guess.
It would decrease, right? Yeah, let's go.
Is that your
And now I
mic?
know
Go,
it
girls.
decreases,
You go.
Is
right?
that your mic?
Oh,
That's
it's
my
not,
mic.
eh?
Yes.
Yes. Are you posting this on Classroom?
Guys, I'm gonna be honest.
Maybe.
I don't know what's different.
I sketched something.
So this is kind of true. I don't know that it would be curved though. Right? Given how this one was a straight up, the one back here was an even line. Right? So I think you're right. It decreases. I don't know that it would be curved. Yes. I don't think it would be curved like you had. Good. All right. So, so what is this going to look like? What is our, over time, what is our velocity doing if our distance and time looks like this? Decreasing, getting smaller. Now, whether this line is curved or not or whatever, I mean, that would be data that would pan this out. Okay, but this is what we are trying to determine in this investigate. These are the concepts and how they're graphically represented. Now in the investigate, you guys are going to do this with actual data. Again, you guys saw that in the thing. Questions on what we went through today? Okay, so